Cool. So we'll be talking about distributed systems, and that term is quite overloaded when people say distributed systems. So if you look at, if you have a microscope and go inside your CPU or a chip itself is a distributed system. You can treat it that way. Or all the cloud services that you use, or products like Kafka and Kubernetes that you use, they are distributed. Or if you go one level higher, your overall architecture, like for a system like Netflix, it is also called a distributed architecture. So what we will be focusing on primarily is around products like Kafka and Kubernetes and all the cloud services. And we'll see why that is the focus. But a lot of principles and patterns that we see, there is typically this quality of self-similarity. When something is a pattern, you will see it at multiple levels of abstraction. So whatever patterns we are talking about today, or I have discussed in the book, it applies at multiple levels of abstractions. So that's the agenda for today. I'll give you some of the background of this work and why I chose patterns as a way of describing or understanding what is called as distributed systems. And then we'll take a look at some real examples of how patterns help us understand some common architectures of common systems. So this is the end product of the work that's happening. That's the book that we published around last year. But I consider this as an ongoing work and periodically getting published on martinfowler.com. The main source of information for this work is essentially going through a lot of open source code bases and try to find similarities and differences and try to articulate those. And more importantly, something is not common. You might be aware of this rule of three that's typically followed when patterns are documented. That something is not called as a pattern unless you see it in at least 3 different implementations. And one other care that we have taken is, unless there is a working example, we actually write some code that demonstrates common pattern across different systems. It is not documented as a pattern. So this working code, and I will talk a little more about that later, why that working code is important. So now as of now, it's a catalog of 30 patterns, and we published a book when we thought that these are good enough set of patterns to explain a full system or to understand a full system, like Kafka or Kubernetes. And I'm taking those names just as examples. It equally applies to any other distributed system that you might be familiar with. So let's start looking into why patterns is an approach or as a method we chose for describing, articulating, and trying to understand these systems. Now I have just listed various tools and frameworks and services that any architecture today, like when we say we are either modernizing a system, going to cloud, hybrid cloud, or your own on-premise systems, you will typically have databases. Like I've listed a few, like a MongoDB, Cassandra, if you are on AWS, Aurora, and there are multiple others that each cloud provider has, and there are so many different products out there. Then there are message brokers. Kafka is the most popular, I think, in last 10 years with microservices and event-driven architectures. Kafka has become like the cornerstone or main building block. But there are others as well. And then there are infrastructure orchestrators, right? You use things like Kubernetes for orchestrating your containers. There are some domains where products like in-memory data grids, particularly popular in the financial domains. And if you are in the data world, if you are a data engineer doing big data projects, there are distributed file systems and products built around that. And then there are hundreds of cloud services that we use every day and that various cloud providers offer. Now, when as a software professional today, if we need to architect any system, or we need to understand a new service or a product that becomes a buzz in the market, the challenge is how to understand all of this. Because we can't really just understand one product and do an end-to-end architecture. And even understanding that one product is difficult enough. And we'll see why. I mean, that's one of the challenges with distributed systems. But what we need to do our day-to-day work effectively is to really understand why these systems or products or services are designed the way they are. What is the reason they are designed the way they are? What problems these designs try to solve? What is the crux of it? And if there are any common problems, because we are categorizing all of these systems as distributed systems, that means there is some commonality to it. And if there are common problems, are there any recurring solutions that will help us understand how they are built? And then when to use these solutions, in what circumstances, what are the trade-offs, and how and when to use them. If we can understand systems at this basic principles level and their basic building blocks level, I think it's a lot easier as a professional developer to navigate through all those names that we saw on the previous slide. Now, how to do that though? And today in the cloud world, with cloud war going on, there is a lot of focus on certifications, right? But certifications, even if they are good, maybe they teach you how to use a particular product or a service properly. It doesn't talk much about why that service or product is built the way it is. And if something changes in future, will there be any changes to expect and what to expect? And then if you need to compare multiple services and products with each other, doing certifications might not be useful. But if you know the building blocks, that's always useful. There is another aspect to it, and I like to use this term called platform sympathy. And I derived it kind of from the term called mechanical sympathy. And you might be aware of this if you know of Martin Thompson and his product called LMAX Disruptor. It was very popular a few years ago. But he uses this term mechanical sympathy and says that whenever you code, whenever you write code, whenever you build any system, or whenever you use any system, it's important to have that mechanical sympathy when you do that. And it's the term essentially is coined by this racing car driver who says that to use and run a racing car effectively, you don't need to be an engineer who engineers a car, but you need to have this mechanical sympathy. You need to know how these various blocks which make a car work together in sync and how to use them effectively. Now, if we translate that to the software systems in the cloud era, that's what the mechanical parts of our data centers, or what we call as cloud, it looks like. So there are hundreds of thousands of servers arranged on racks. There will be power supply and network cables, you can see. I mean, this photo I have taken just one random photo from Google data center photos, but you will find some fascinating photos if you just Google for data center photos. And whatever products, services, or architectures we build in today's era, they essentially are built the way they are because they run on these kinds of environments. And we need to cater to the realities of these environments. And that's the reason they are built the way they are. So to use them effectively, if we know what are the realities of these environments and what are the building blocks of these products which cater to these environments, we can use those products a lot more effectively. And it's also easy to understand why they are built the way they are. Now, how to achieve this platform sympathy? Do we read books? That's not enough a lot of times because there is a lot of gap between theory and practice. Whenever you read something or hear someone speaking, like I'm talking right now, and for that, I follow guidance of two quotes that I'm going to show. And this one is from Martin Fowler, and he famously said that code is like mathematics of our profession, and that's where you remove all the ambiguity. And for this reason, actually, a lot of earlier talks that I did while I was working on these patterns, I never did any PPTs. I mostly showed code, working code for most of the talks. The other interesting quote, this is not a quote really, but a part of another patterns book, older patterns book called Organizational Patterns. And it has this interesting pattern, a well-known pattern, by the way, called Architect Also Implements. And it has this nice comment on abstractions, and which is very important today when there are so many things or so many efforts done to abstract away a lot of complexity from us. And what this comment says is abstractions are nothing but disciplined form of ignorance. And we need to be aware of that because abstractions we create abstractions to ease our lives, to make our life easier, to speed up the work that we do. But we need to be aware that they are ignoring certain things, even though in a disciplined way. And a lot of times, the failures that happen while using these systems or using these products or even when we architect certain systems, they always happen on the details that we try to hide or we try to ignore. So we need to be aware of what those details are. And as we saw on the previous slide, when we write code, that is when we can actually unearth or actually see through what's going on behind those abstractions. So let's say, and I have been talking about Kafka and Kubernetes just as examples. So just a show of hands, how many of you are using Kafka in your work? Okay, a few. And any of you using Kubernetes? Okay, a few. And people who are not using it, are they indirectly using it? Indirectly, yes. Cool. So let's say I talked about platform sympathy and building blocks, and a way to understand that is only to code, let's say. So if we are using Kafka and Kubernetes, and we now try to use this patterns approach to really understand things in details, and maybe to by writing our own Kafka and Kubernetes for learning purposes, not necessarily for production use, so that we know, we saw that platform sympathy slide previously, right? So so we know what the building blocks are, what is the interplay between them, and maybe to make right choices and take right decisions. Can you do that? So that's where this patterns approach comes in very handy, because it's a good mix of description with some code. And why that is useful is that patterns, when you structure things as patterns, or structure information as patterns, or you try to articulate your understanding as patterns, the structure of that patterns is pretty generic. So you don't describe something that applies only to Kubernetes, or you don't describe that applies only to Kafka. It needs to be broad enough to apply to multiple systems. But on the other hand, it should be specific enough to show real code. And that's the beauty of patterns as an approach that I find, because when something is as concrete as you can actually write code, and not pseudocode, actual code in Java, C++, or whatever your favorite languages, a lot of ambiguity that you face just when you read English documentation, it goes away. The other important aspect of patterns, and you might have heard this multiple times, that naming things is one of the most difficult problems in software world. But patterns, when you read or when you yourself structure, they have some well-established names. And well-established names with some concrete code structure that's associated with it. And that's a very powerful thing to have. Because when you have a well-established name with a very concrete understanding at the code level, and you know multiple of these patterns and how they link together, you actually can think of the overall architecture as a sequence of patterns. And you know, because you know how patterns play together or how they work or interlink together, it becomes easy to understand a particular architecture. So for example, if we want to understand how Kafka is built, and you know a set of patterns, like I said, there are 30 patterns, you can very well, and you know how those patterns play together or link together, it's very easy to understand Apache Kafka's architecture. So let's take some example now. And I've been using Kafka and Kubernetes as examples. So let's say we are let's say reading Kubernetes documentation and we are reading Kafka's documentation. And we see sentences like this, that Kubernetes has something called as control plane, and it uses etcd as its backing store. And Apache Kafka, it needs Zookeeper, or the newer version, it doesn't need Zookeeper, but it has something called as a controller cluster. And we now want to make sense out of these. What does this mean? So let's say at high level, if you say Kubernetes is essentially used for orchestrating containers or pods, which is group of containers on multiple machines. So you have multiple servers, which I'm calling nodes like this. And then you have a smaller cluster, which is etcd. etcd is a product that Kubernetes uses. And then if you read about etcd, there is a mention of something called as Raft there. If you see Apache Kafka, again you see something similar, that there are multiple nodes or multiple servers, but now instead of containers, there are topics and partitions. And then you again see a smaller cluster, which is Zookeeper. Zookeeper is the product that Kafka uses. And if you read about Zookeeper, there is this mention of something called as ZAB. And then, I mean, just to show the similarity with anything else that's called as distributed. So any other database you take or any other cloud service you take as an example. And you see how that looks. It has these multiple nodes. Again, now there are, because we are talking about database, there are tables and not topics or containers. And then there are shards, which are splits of your tables or partitions of your tables. And then again, you see something like that smaller cluster, which is called as master cluster. And they have their own implementation for that master cluster. So don't use Zookeeper or etcd. And if you read about that master cluster, there is also this mention of Raft. So you see that all the three examples that we saw and the English documentation that we saw, it has this similarity, right? There is a larger cluster, and then there is a smaller cluster. So if we understand why there is this separate smaller cluster and why not just one cluster, it's easier to understand what's going on. So what does this smaller cluster do? It manages metadata of the cluster. So which partitions are on which nodes or which containers are running on which node, stuff like that. It helps implementing what is called as leader election. So if one of the nodes that we saw needs to act as a leader or a controller to take decisions on behalf of the cluster. But to implement all this needs what is called as consensus implementation or consensus algorithms to be implemented. And they don't scale well beyond a few nodes or beyond a cluster size of say 3 to 5 nodes. And that's the reason the solution typically always is that you have this smaller cluster for managing your cluster metadata and have certain primitives that we'll see to which then can be used by your actual data cluster. And you can see that your actual Kubernetes, Kafka, or other data cluster, you will have typically, the size will be in thousands of nodes or thousands of servers, and your smaller cluster will typically always be 3 to 5 nodes. So to allow that cluster to scale to thousands of nodes, you pull out this smaller cluster like this. And then if you see a pattern or what commonality you see in there, you describe that as a pattern, and pattern is called as a consistent core. And pattern, as you know, typically has this problem and solution parts. Problem describing why what is the challenge that you are trying to solve, and solution gives you a solution structure. So managing metadata with strong consistency using consensus algorithms so that your main cluster can independently scale to thousands of nodes. And for doing that, for achieving that, you use this smaller cluster for your metadata. So once you know that there is a concept of consistent core, and that's how typically your cluster coordination is managed. Practically any distributed system, cloud scale distributed system, you will see that it has this kind of a component. And different documentations and different products will call it by different names and maybe have slightly different descriptions of it. But once you know what this is, it becomes a lot easier to understand. Now, we said that there are patterns are not generally used alone, right? There are multiple other patterns that this pattern links to achieve a broader goal. So how is this smaller cluster used? So we said one of the use cases is to do a leader election, or to choose a controller from your larger cluster. But whatever mechanism you use, like once you choose someone as a leader or someone as a controller, it should not be for indefinite time, because failures can happen at any time, and you cannot give indefinite access of any responsibility or any resource to one particular node. And the solution to that is to grant time-limited leases. So you grant access or grant lease, something called as lease, but you keep that time bound, so that in case of failure, and we'll see how, but whoever wants to play a particular role, let's say, like this node 1 can say that I want to have access for this node 1 name. And it can register a lease with that name. And that's a typical interface that you will find on the products which are consistent cores. And then the responsibility of this node is to refresh that periodically. And if it's not refreshed, let's say, beyond a certain time interval, it's the consistent core that will consider that the lease is expired, and it will remove that lease. So this is another pattern you will always typically find along with this consistent core, or the interface of that consistent core will almost always have this feature called as lease. So if you see Zookeeper or etcd or master cluster or any other product or any other custom implementation that's used as a consistent core, will have a mechanism called as lease. So are there any more uses of this smaller cluster? So one other common requirement is that because this smaller cluster is now managing your cluster metadata, and you have this, let's say, thousands of node bigger cluster that's out there, multiple nodes in that cluster now need to know if there is change in configuration or change in metadata, and it needs to get that real time. So let's say this node 1 we saw, it registers a lease like this, and some other nodes, they need to know if there are any leases registered under this prefix called server. So are there any servers registering lease with the consistent core? With this, there is a mechanism by which this consistent core can notify the nodes which are interested in that information. So this ability to be able to register your interest for a particular kind of data and to get notified when any change that happens in that data is again a common pattern, which is called a state watch. I mean, that's the name. So you're watching the state on a remote server. And whenever a node needs a real-time update for any change that happens, you need ability to register an interest and then get notified. So you can see that this consistent core, along with lease and state watch, is often used together for doing cluster coordination and cluster metadata management for practically any distributed system. So whenever you read something like Kubernetes control plane or Kafka using Zookeeper, you can see interplay of these three patterns together. And to understand the Kubernetes or Kafka control plane, you can understand it in terms of these three patterns. Okay, so I talked about ability to code based on this understanding of common patterns. So I will show you some code, but these are the repositories that I use to run a few workshops where we build products like Kubernetes or Kafka from scratch in a couple of days. But whatever we just saw, I will probably just show you the. So this is Apache Kafka source code from GitHub. And once you know that you have this concept of consistent core with the concept of Lease, that in case of Kafka, it will be brokers, that the servers are called as brokers. You see that whatever we saw on the diagram, right? You see very similar code out here. So it's if you see what's okay, it's right here. So whenever your broker start or a server start, they register with Zookeeper, which is a consistent core. And Zookeeper has this concept of ephemeral nodes. So we talked about leases, right? Zookeeper calls them as ephemeral nodes. So they go away if they are not refreshed, or the session client session expires. And once you know this, it becomes a lot easier for you to, because there is a lot of complexity in making a system production ready. But concept level, you can, it's pretty simple in a way. So if you see these two repositories that I will show. So this is a Kafka or a miniature Kafka. And that's how we also, when I documented patterns, that's what I did as well, like created my own miniature versions of all the products that I studied. So this is a end-to-end Kafka, and you can see that, I mean, Kafka in the sense my own Kafka, but it has everything that your actual Kafka has. And the advantage of doing stuff like this is you have your own miniature playground where you can try out different things. So this is single JUnit test that is running a Kafka cluster. And you can actually simulate, let's say, having a larger cluster or smaller cluster and introducing failures. And you also see the interplay of, because you actually code it yourself, you see that whenever you create a topic or whenever you produce a message, what happens underneath. So I encourage you to try this. I mean, you look at that GitHub repo and maybe give it a try. And similar to Kafka, this is a Kubernetes repo that I have. And similar to that Kafka test that was out there, this is a Kubernetes test, essentially doing the same thing, setting up, building a Kubernetes from scratch, has same components that a typical Kubernetes implementation would have. And you can set up a cluster yourself and say try orchestrating the containers. So do give it a try. So just to summarize, I mean, that's summary, I mean, the patterns is a tool for achieving platform sympathy, but platform sympathy is something that is very crucial. And one of the interesting observations that I have been having in last few months is that once you understand concepts at patterns and principles level, right, using generative AI tools is lot more effective. Because you saw like one code, Kubernetes code is in Golang, and Kafka code is in Java, and maybe you use Rust for something else. You can interact and instruct a tool like Copilot a lot more effectively, and also validate the output code a lot more effectively if you know those concepts at patterns level. So there is another aspect of this, and you might have heard this term called accidental complexity and essential complexity. Accidental complexity is, so essential complexity is the real complexity of your system, just inherent complexity. Just when we say distributed systems, there are failures, things need to work on, say, thousands of servers, and that's inherently complex. But there is this accidental complexity that is introduced just because the way the code is written a lot of times, and that makes it a lot harder to understand certain things. So patterns help in this sense as well, that once you understand patterns well, that accidental complexity is a lot of times reduced. But you actually see what essential complexity is. And that's very important, because when you use abstractions, like you use something like Zookeeper, and if you read the documentation, a lot of times you will probably feel that all the problems are solved for you, or when you use a cloud service, they might say that all the problems are solved for you. But there is this essential complexity that we need to be aware of. And it's a lot of time buried in documentation and other things. So patterns also help you with that aspect, that they clarify that essential complexity, and it helps you to think through clearly. So that's about it. You can explore more patterns. I mean, I just covered some very simple things like cluster management, relatively simple thing, but there are a lot of other patterns that you can explore, particularly patterns around distributed consensus and stuff like that. But I'm open to questions.